observed simulation. The first speaker is Linda Tacconi, star formation and gas scaling relationship from Z equal 2.5 to the present. Thank you.
Okay. Thanks very much, Piero. Thank you as well, organizers. It's great to be back. We missed a year. And so what I would like to tell you about this morning is what we know about the gas contents, the molecular gas contents of galaxies as we move from the local universe out to redshift 2.5 or 3. So a couple of years ago, I gave a talk here on a similar topic, and at that time we had about 50 star-forming galaxies between redshifts 1 and 2, where we were starting to assemble the molecular gas contents through single targeted measurements of CO. So today, I want to show you the progress that we've made since then, and which is actually quite substantial. We've almost tripled the number of sources for which we can detect CO at higher redshifts, and we are also now looking at scaling relations. So how is the gas evolving as a function of redshift, as a function of specific star formation rate, as a function of stellar mass, and other key parameters that all play a very important role when we're trying to understand how galaxies evolve from high redshift to the present. So the highest redshift I'm talking about is 2.5, not the super high redshifts that we discussed on the first day. So this is work that I've been doing together with many people. In particular, I want to highlight Reinhard, François Combe, Roberto Neri, Santi Garcia Perillo, Alberto Bellato, Natasha Förster-Schreiber, and Simon Lilly, who are sort of doing an awful lot of the work, but then we have a large team, as you can see here in blue, many of whom are sitting here in the audience. So what have we been doing? We've been observing mostly with the IRAM telescope, now called NOEMA, which currently has 7 15-meter antennas. It's being upgraded to include 12 antennas, so when this upgrade is finished, it will have the detection capability of between 30 and 50% of ALMA. So it's very important for northern hemisphere fields, such as the Aegis field, which people here have been working on quite a bit for a very long time. Also GOODS North, and so many of our very popular deep fields are in the northern hemisphere, and this upgraded instrument should be interesting for people who are working in those fields. So what have we been doing? It's a program which we started several years ago, but we now have a legacy status, so we're working in the middle now of a 1,000-hour program with the IRAM telescope, targeting redshifts of 0.5 to 2.5 and targeting galaxies that are mostly on the main sequence. So since 2 years ago, what's really changed is that we have now got a substantial number of galaxies in this intermediate 0.5 to redshift 1 range, which we didn't have before. And also we've been able to probe slightly below the main sequence at the higher redshifts. I should say we're selecting only on stellar mass, so we're targeting the massive population at all 3 redshifts, so a few times 10 to the 10th and higher, all the way up to into the 10 to the 11th solar mass regime. What we don't get at this point are beautiful images like what you see here from HST, which are some of our targeted sources. What we do get are good integrated spectra of CO, as what you see here. We're still at several arcseconds resolution in most cases. But we're ready for follow-up. We have done follow-up both at IRAM now and at ALMA in some of our targets. So that we will be able to push to well below an arcsecond. And at the very end, I'm going to show you 2 cases, which I think, given the discussion yesterday, should start the discussion for today on where we think we're now starting to see evidence for this compaction process. So just one more point. We've observed about 125 galaxies by now and detected over 90% of them. So this plot shows you then, through CO, where we are now in our ability to interpret the evolution of molecular gas. So this plot shows you specific star formation rate relative to the main sequence. So that's this swath here in the 2 dotted lines as a function of redshift. And the different symbols show you the different surveys, both from our work, which is called FIBS, also other work in the literature that are listed here, and also the references are given below here. And so if you combine all of these surveys together, in particular our survey plus the cold gas, the local universe survey led by Guinevere Kaufmann and Amélie Santonge, then you see we have over 500 galaxies through CO. If you then take the beautiful work that Herschel has given us on the dust so far, so this is work that has also been done by our group at MPE, but also by David Elbaz and his teams, and Emmanuel Haddadi in some papers here. Through Herschel stacks that are shown here in green, we can get to the molecular gas also by way of the dust. So if you look at these different points, you can see that we're starting to fill out the main sequence very, very well at all of the redshifts where we sampled, in particular at local universe, of course, but we're actually doing almost as well in the local universe now and the high redshift universe as we do locally when you take Herschel and the CO work combined. Of course, below the main sequence, most of our information comes from the local universe, more so than the high redshift universe, but both with IRAM and with ALMA, we're starting now to probe below the main sequence, even at redshift 2. So, as I said, our main goal is to start looking at the evolutionary traits of the molecular gas as a function of redshift, specific star formation rate, and stellar mass. And as sort of a parallel to that, we also want to look at the gas consumption timescales also as a function of those three properties: redshift, specific star formation rate, and stellar mass. So what you can see here on this plot is the gas fraction that we now have, the average gas fractions as a function of redshift, both from the CO methods, where you take CO and convert into the molecular gas mass, or by the Herschel dust method, where you take your fluxus fit SEDs and convert to, assume a dust to gas ratio, and you convert to molecular gas that way. And I think what you can see is we're seeing a very strong trend with redshift, and also that both the dust and the CO measurements agree very well in most cases, especially in the averages. So since we now have a well-defined evolution with redshift, we can then look at some of the dependencies on other things. Mm-hmm. No, this is the average. These are the averages. So this is what the error bars here are supposed to give you an indication of the range in masses that we're seeing at each of the redshifts.
Just to clarify though, at C of 2, the points there are not on the graph at C of 0, correct?
I don't understand.
Because they will have gained in mass.
Yeah. So these are not, the redshift 2 points are not.
Following the mass evolution.
No, exactly.
That's what
Yeah. Yeah. We're targeting the massive population at all redshifts. We're not following progenitors of the Milky Way out to redshift 2. That's impossible because of metallicity effects, which we can talk about later on in the discussion. Okay, so if you account for the trend with redshift, we then can look at the gas. Here we plotted as gas to stellar mass ratio as a function of specific star formation rate, where the main sequence is this vertical line here. And the blue are the CO measurements again, and the red are the dust measurements. And here you see a very strong trend of molecular gas fraction versus specific star formation rate, where those galaxies that are above the main sequence have higher gas fractions. And that is seen at all redshifts because this is all the redshifts now plotted on top of each other. If you then account for that very strong evolutionary trend with specific star formation rate. You can look at the residuals there and take our third parameter, which is as a function of stellar mass. And there you see something very interesting, which is that once you get above 10 to the 11th solar masses and stellar mass, the gas fractions start to drop. And that, again, that's been seen in the local universe in the cold gas survey. We're seeing it now at all redshifts. And that is tantalizingly similar to where you see the flattening in the star formation main sequence, where Reinhard showed you where you're starting to see these massive ionized outflows, perhaps throwing gas out of the galaxy. So we may be seeing this in the molecular gas as well, that as you go to higher masses, the gas fractions drop. We then can also look, as I said, at the gas consumption time scale as a function of redshift. And here again are points from our work. This is from a paper that Reinhard was the lead author on just a few months ago in the CO and in the dust. Now this is referenced to the main sequence. So this is depletion time scale referenced to the main sequence. So this is not accounting for above main sequence galaxies. Now there's another point here from Mathieu Betemann, which I think shows you the very similar trends. And here what we're trying to show is that the depletion time scale actually for us, surprisingly, is not dropping very steeply, as you might expect if things like gas consumption are driven by large-scale dynamical motion. So we would have expected perhaps, and I think maybe some of the simulators would have expected that this trend would be dropping as the size evolution, as the size of the galaxy, but it doesn't seem to be. It seems to be much shallower than that, which I think makes some of the more local theorists happy. Mark is not here right now, but one of the things that this may be telling us, oh, he is, okay, great, is that the star formation, what's setting the consumption time may be a local process, not a large-scale process.
What's the local process?
Well, Mark will tell you it just has to do with the local free fall time of the clouds, right?
It doesn't help all the way.
Yeah. Well, I think that the fact that there's something physical that this is telling us. But one thing that for sure it's telling us is that we need to be replenishing gas at all redshifts. So accounting for this redshift evolution, then, and we can again go through the same exercise with the specific star formation rate, where again here is the line, the main sequence line. So here are the starbursts over here. And what you can see, what this plot shows you is that we have a very strong evolution of depletion time with specific star formation rate. So not only are the gas fractions higher as you go above the main sequence, but the depletion times drop dramatically as you go above the main sequence. So there's more gas to process into stars, and it processes them more efficiently, if you like to think of it that way, as you go above the main sequence. On the other hand, this is something that, I forget who was discussing this yesterday, as you go below the main sequence, we do see increased depletion times below the main sequence. So this is our strongest trend of all the trends. With stellar mass, we don't see much of a trend, so I don't have a plot to show you that in this talk. So this is, as you can say, we're now able with this 1,000 galaxies to look at the basic trends with stellar mass, with specific star formation rate, and with redshift, and be able to look at how gas is evolving. One point that I forgot to make here, one of the things that this may be telling us here is that the dense gas fraction, this is a plot of HCN over CO, which is thought to be an indication of how much dense gas you have versus how much just more quiescent molecular gas. And this is for local ULIRGs. And you can see that as you go above the main sequence, there may be a trend here where the dense gas fractions increase for those galaxies above the main sequence, so in the starbursting mode. We haven't been able to test this yet at high redshift, but that's certainly one of the things that we will be doing. Yeah.
Could you just clarify the definition of the y-axis in the right-hand plot? It's normalized.
It's normalized to the main sequence. So it's at the
main sequence.
yeah.
Okay,
Okay, so galaxies are more gas-rich at higher redshift. Now, just this is a plot that I think hasn't been shown yet, so I just wanted to show it quickly. You've heard the term, I think, a lot in this meeting, that high redshift galaxies are also turbulent. The disk galaxies are not the same disk galaxies as we see locally. This is work, this plot is from Emily Wisniewski's paper. This is something that has been thought about here in Santa Cruz for a while. The paper by Susan Cassin addressed this very nicely as well. There's a lot of people looking at this now. So what this plot shows is the average dispersion as a function of redshift. Now, in these marginally stable disks, you expect that this redshift, the velocity dispersion, is a function, is dependent on the gas fraction. Now, if you recall what I showed you before, the gas fraction evolution with redshift, it looks very similar to this. And so these high turbulences that we see at high redshift are a natural consequence of the fact that the gas fractions that we're seeing there are 50 or 60%.
So is this sigma determined from pure cosmos or measured sigma?
This is measured sigma. This is all in all those cases that Reinhardt talked about where we have good enough data to be able to measure an accurate dispersion in the outer disks.
But it's consistent.
Yeah. So I want to spend, how much time do I have? 5 minutes. Okay, I want to spend 2 minutes then on the Kennecott-Schmidt relation, which I think you all know about, relation between star formation density and gas surface density, and what this, in the local universe, has been a lot of discussion on whether what is the slope, and this is used a lot by high redshift observers who don't want to observe gas directly. And so it's important to understand what the slope is and what are the causes of these nonlinear slopes. So this is the latest version from Kennecott and Evans in their review. Other people, in particular listed here, have shown that it's actually a more linear relation. Once you take out the effects of H1, that you get a linear relation. We had also seen that 2 years ago, that there was a linear relation in the redshift 1 galaxies where we could do our own Kennecott-Schmidt fit. And here's an update now with all the galaxies that I've showed you before. Now, we don't have sizes, so this is not the surface density relation. This is the integrated relation, so it's just star formation rate versus molecular gas mass. What you can see here is that there are lines of constant depletion time scale where you have in red the above main sequence galaxies, in cyan the slightly above main sequence galaxies, in blue and gray main sequence galaxies, and in black and brown below main sequence galaxies. At a given specific star formation rate, what we're finding is that you get a linear relation. And the superlinear relation comes from the fact that in the past, people were putting together things like ULIRGs together with things that are below the main sequence and getting this slightly nonlinear slope. Now, you can get an above, so you have to be very careful when you're making one of these plots what you include. And we would advocate that you want to, depending on what your specific star formation rate is, you want to look at the galaxies that have a similar specific star formation rate. Because in the past, people were also more or less talking just about the ULIRGs versus the normal galaxies. We were getting something that looked like a bimodal relationship. That's gone away now, that we include things that are slightly above the main sequence. So the takeaway points on that is be careful. the dependence, the strong dependence that I showed you before on specific star formation rate will result in this superlinear slope. At a given specific star formation rate, you get a linear, near linear regime. But the caveat here is that we haven't been able to account for the scale height of the gas. And you can go back to slightly superlinear if, as Mark says, you want to actually look at the volume densities. We don't have those.
I can't tell whether you're taking aim at superlinear using molecular gas or superlinear using total gas, a la the latest update.
Well, they were getting superlinear using both total gas and molecular gas but you get superlinear with only molecular gas when you include these together with these.
Do you have an opinion about superlinear versus total gas?
We think that you should always use molecular gas because that's what the stars are forming from. Okay, so in the last couple of minutes, then I want to show you some very new data in two sources, where here is galaxies where we have, in this case, we have a beautiful symphony plus AO H-alpha data set. This is one of the targets that Reinhard showed you the other day. And what you see is here the compact nugget with an effective radius of about 2.5 kiloparsecs. You see an H-alpha outflow here in red, and in blue you see the HST H-band image. In green you see the H-alpha narrowband image. On the bottom panel, you see the same in CO. Our current data are at a resolution of 0.7 arcseconds, so about factor 3 worse than what we're getting with the adaptive optics with Symphony. We've just been awarded time in cycle 3, however. To rectify that, we will now, with ALMA, get below 0.2 arcseconds resolution. And what we see is a narrow component. This is the integrated CO spectrum here. This is the integrated H-alpha spectrum here. And this, what we call the narrow component here, is shown in green. In red, we see a CO outflow. This is this broad wing here, which is zoomed up here. And there may even be a slight blue wing. This system has 3.5 times 10 to the 11th masses of molecular gas at extremely high surface densities, so comparable to what we see in local ULERGs and well above this so-called Barrow criterion that Guillermo was talking about yesterday. The powerful outflow is seen in H-alpha, but we are also now, we see it, we think, in CO. We will go deeper and try to elucidate the molecular outflow. This is a supermassive galaxy. It's got a stellar mass of over 10 to the 11th, and it's still forming stars. So this is a good case for one of these blue compacted galaxies. Here's another one, this one now at redshift 1. This is an Aegis, so we don't have a good H-alpha map, but we can plot both this is the HST in green. Here is a submillimeter dust continuum map that we got at IRAM together with the CO map. Here now we have a resolution of 0.3 arcseconds in CO, 0.35 arcseconds. We're seeing that the main CO is very consistent with a rotating disk, but a compact rotating disk. Here again, lots of molecular gas within a few within a very small region of a few kiloparsecs and a high rotation speed. So again, here again we see a case for a compacted galaxy. We also see evidence for molecular outflow. So we are starting to see these things also in the molecular gas, but this is very early, very, very early days. We only have 2 cases. We will hopefully get some more. So I'll just put up my summary and stop there. Yeah.
There's like the gas fraction. Actually, one of the striking things was the huge dispersion at each redshift, if I read that plot well. Can you comment on that? Because together with, I had the impression from what you said that the gas fraction is actually doesn't have a huge, huge
the gas
dispersion.
fraction does have a huge dispersion as you go above and below the main sequence. There is a huge dispersion.
So the plot you were showing with the small arrow bars, when Frank asked, I got the impression that the averages are no. So can you comment on the large dispersion on the velocity dispersion plot at each redshift?
It includes some of these high dispersion galaxies as well as some of the larger disks. There's points of everything. I don't know, maybe Reinhardt wants to comment because this was a plot.
This is regarding the same relation. I was just wondering, the interpretation in terms of this has anything to do with the tumor stability criterion kind of only makes sense if you're actually measuring this velocity dispersion on always the same scale. And I could imagine that at higher redshifts, poorer resolution, you're measuring it on larger scales, and that could boost the velocity dispersion function of redshift because basically there's a Larson relation, and because you're now basically convolving over a larger dynamical range of the galaxy. So to what extent do we know that this is really can be interpreted safely as having something to do with the tumor?
In all cases, those measurements, as far as I'm aware, were taken in outer parts of the galaxies, so where the rotation curve is flat-ish. And after subtracting out the rotation component. Now, yeah, there's slight effects of size, but here we're not talking about cloud scale dispersion measurements. We're always talking about things that are on scales of more than a kiloparsec. So I would guess that that's all averaged out.
Okay.
Last question.
I'll just share. So I was thinking about metallicity effects. So I'm glad that you're sort of cross-checking the CO and the dust. But I'm wondering, okay, so if I lower the metallicity, then that has the effect of I lower the dust to gas ratio. So for a fixed IR luminosity, I should infer more gas mass. If I lower the metallicity, then the CO luminosity goes down, and again, I should infer more gas mass. So to what extent are your, so unfortunately they don't completely cross-check each other, so to what extent are your results sensitive to the metallicity you're assuming?
We make the same assumptions in both cases, plus we're targeting the massive population. So where the metallicity effects, even at redshift 2, should be minimized. This is the main reason we put in our mass cutoff of about 5 times 10 to the 10th solar masses and stars. We're also correcting, we are making a correction now for the metallicity effects as we know them at all the redshifts. So we are trying to take that into account.
So what sort of metallicity range does your sample cover?
They're all about 0.7, 0.8 solar and higher.
Okay.
That's a bias, but it's because you get into very, very murky waters if you try to get out of that bias.
Okay, let's thank Linda again. Next talk is by Alison Strong.